In the last lecture, we have started discussing about the MOSFET. Okay, so we will see different types of MOSFET in this lecture. Okay, so the NMOS and PMOS. So if you see here, basically what we have seen here, the channel form of the electrons. Okay, by applying this positive potential, we have attracted electrons. So a channel of electrons is formed. It is also possible that we can make channel of holes. Okay, we can make channel of holes by using a similar kind of phenomenon. Of course, then we need to change N to P and P to N. Okay, let's see this another type of MOSFET. So this kind of MOSFET where we have formed the channel of electrons is called NMOS. Okay, this kind of formation of the channel of the electrons, which is negative, is called NMOS. So we will see the types of MOSFET. So there are two types of MOSFET. One is the NMOS and the other type of MOSFET is called a PMOS. The one which we have been discussing now till now is this NMOS. So okay, let's focus on NMOS again. Let's revise what we have discussed before. So this was NMOS. Okay, so where we had all the potentials, right? So the source, drain, and the current was flowing, and of course the channel was becoming tapered finally. Of course the channel is tapered, and we also have discussed about the saturation region, linear region. So this is NMOS. Okay, so now we will discuss about the PMOS. Okay, so in case of the PMOS, everything will get inverted. Everything will get reversed. Okay, so the N will become P and P will become N. So this is my PMOS. So let's for time being let's not apply any voltage here. Okay, we'll see this one. Of course, this also should have a bulk terminal, and of course there will be source and drain. So we will see this. Okay, so okay, so I need to reverse. Okay, so instead of p-type substrate, there should be an n-type. Okay, so I should have an n-type substrate, and actually for PMOS it's called sometimes well. Okay, we'll see why it is called like that. Okay, it's basically the n-type substrate only, so maybe time being just remove this well. Okay, and this will be of course this will be p-type, p plus, just the reverse, p plus, and of course now I'm connecting to the body, so this should be n plus now. So now the this two p plus and p plus is connected to the ground. Okay, so now in case of the PMOS, P stands for the positive or the holes. So I want to attract holes. So I want to attract holes here, okay, beneath the channel. The reason is that we want to have the conduction by the holes. So I have this P plus island here, P plus island here, and if I attract the holes here, so there will be a nice conduction that will happen, right? From here we also have the majority charge carrier as holes, and here also holes, right? But then if I want to attract holes, holes are positive in nature, right? We need to apply a negative voltage here. Okay, we need to apply a negative voltage here. Okay, so my VZ, whatever the VZ voltage that I will be applying, it has to be negative. Then only the holes will get attracted. Okay, so yeah, so this type of transistor is called PMOS device. Okay, so now, however, generally the question comes is that will I get always negative voltage in my application, right? Will I get always negative voltage in my application? So mostly it may be no, because the battery that we may use may be 0 to 5 volt. Okay, or or whatever, 0 to 2 volt, 0 to 1 volt, right? So we will not get negative voltages always, and we will get only one voltage. It may be possible that we can arrange negative voltage, but it is not very convenient. So instead of that, so if we want to use this PMOS, and if I want to generate this negative voltage, so here it means that this negative means it's a relative, okay? It's a relative in the sense that this is what it means is that this should be this negative voltage. It means that this point is a lower potential compared to all these three potentials, okay? All these three potentials, okay? So now so the way it is done is I can put all of them it as at a higher potential, and I will apply a voltage Vg which is lesser than VDD. Okay, so basically I am shifting up all the potential levels. Okay, so then this also, if I shift this one, this Vg by a VDD, then this also will come into positive. So ultimately what it matters is from here to here it should be negative. The VGS should be negative. So, and this is done something like this. So instead of applying a negative potential here, I will be applying a positive potential VG, but then I will connect all this one to VDD. Even the bulk also I'll connect to VDD, and maybe this to VDD. Okay. Okay, so of course now this Vg should be, it's a positive voltage. Vg is greater than 0, but it is less than VDD. Okay, so now because this Vg is lesser, so now my VGS, if you see the gate to this drain source, okay, gate to source will be, gate to source, now it will be negative. Okay, VGS will be negative, so we can call this as a drain. Okay, so now I want the current to flow in this direction. Okay, so what I need to apply is that I need to apply a potential Vd, right? Potential Vd, and this Vd also will be lesser than Vdd. Okay, it will be lesser. So this is at high potential and this is at lower potential, and of course the direction of the current is from the source to the drain, ID. Okay, so the direction of the source is from the direction of the current is in this direction. So and of course it is same like the this is acting as a source for all the carriers, right? So this is opposite to what we have discussed in case of the NMOS, because the carriers are electrons there and the direction of the current is opposite to the direction of the movement of the carriers because they are electrons. But holes are positively charged, so direction of the current is same as the direction of the carrier. So we can see that the charge starts flowing from here to here, and of course again the same principle happens again. There also will be a tapering. Okay, so basically my channel will be tapered. So the same principle applies. Okay, everything is same, right? All the equations and all is same for both NMOS and PMOS. Only there's a slight difference in the mobility. Okay, so now when we write instead of mu n, we have to write mu p. Okay, so this is what we will discuss eventually. Now the other thing is for these n PMOS, for this PMOS, the bulk potential, the bulk terminal B has to be connected always to the highest terminal, highest potential of a circuit. Just like in case of the NMOS, it was connected to the lowest potential, so to avoid the PN junctions to be in forward bias condition. So if I connect this one at the highest potential, so whatever this N and this P, right, it will always be in a reverse bias condition. Okay, so this is the condition that we need to follow. bulk terminal of PMOS should be always connected highest potential in a circuit so that the PN junctions are never turned on. Okay, so now in this case, if I want to write the two equations, right? So if I want to write these two equations, um, you know, I have to make sure the equations are right, but here the polarity is going to become different. The VGS is negative in this case, right? Because my VG is lower than the VDD. But this is quite confusing. Even the threshold voltage is negative here, right? We need to get a negative voltage here VG for turning on the device. So instead of that, many textbooks will show you that the threshold voltage is negative, VGS is negative. So this is quite confusing. So instead of that, what we'll use is we'll see only the absolute potential, okay, absolute potential, and we'll try to write the same equation for the NMOS, for the PMOS, just like the NMOS, okay. So all the equations remains the same, except the only difference is that we are considering only the magnitude, okay. So this is we have to remember. So again, let me write the equations. So in case of the cutoff condition, of course, in this case also ID is 0, and my VGS, again I'm writing the mod, okay, because VGS in this case is negative, VSG is positive, so it should be lesser than the threshold voltage. So then it is in a cutoff condition, no channel is formed, okay. So it's the same as for the PMOS, okay. So linear region, again the equations are same. Only the difference is that mu p CMOS W by L, okay, and here VGS, mod of VGS minus mod of VTH into VDS mod minus half VDS whole square. Note that in this case the VDS is also negative, D and S, because S is at higher potential compared to the drain. So we need to take again the mod in this case, okay. So all the equations are valid only in the case that we have to take mod in this case. So again, for this linear region we have VTH, that my VDS is still very small, VDS is still lesser than VGS minus VTH, and in the saturation region my ID is given by half mu n CMOS W by L VGS minus VTH whole square, and in this case my VDS is greater than VGS minus VTH greater than equal to, okay. So again here if you observe, we are writing the same equations that we have written for the NMOS. Only thing is that we have taken a mod because of the change in the polarity. So that's the only difference that we have to consider while discussing the PMOS, but it is the same. Only here the mobility is different. Here mu n and mu p. Mu p because the charge carrier are now holes instead of electrons. Okay, so instead of electrons, it is hole. Sorry, this is not mu n. This is mu p again. So I take it back. Okay. And as we know that to the mu p is approximately 2.5 times smaller than mu n, as we have discussed when we started discussing about the mobility of the p-n junction of the p-type and n-type material long back, when we are discussing about the semiconductor physics. What we have seen is that this mu p is approximately 2.5 times smaller compared to mu n. So since mu p mu n by mu p is equal to 2.5, right? So to make PMOS same as NMOS, so I want to make PMOS and NMOS behaving the same way. So actually, in case of the CMOS, NMOS and PMOS, the COX are always same because they are manufactured in the same time, and this is basically based on the thickness and the material, so they are the same thing. So COX is same. So only thing is for a designer, what is remain is this W by L. So to make PMOS same as NMOS, W by L of PMOS should be 2.5 times higher than that of MOS. So this is very important. So this is especially important, and this thing will come again and again. And this is a very common question asked in interviews, that if I want to make this NMOS equivalent to PMOS, what should be the ratio of the sizes? So it comes from this expression that because the mobility of the PMOS is 2.5 times smaller than the mobility of the electrons, right? So that's why the size of the PMOS, which is based on the conduction of the holes, is 2.5 times smaller, sorry, 2.5 times larger to get the same property. Okay, so now in most of the technology, both the NMOS and PMOS will be there. Okay, so both of them has a different advantage. Okay, and they complement each other. So this is called a CMOS technology. You must be hearing the different CMOS technology, IC fabricated in CMOS technology. What it means is that this CMOS technology provides both the NMOS and PMOS on a single substrate. Okay, so let's see how it does. So in a CMOS technology, I have this P-type substrate. Okay, P-type substrate is there. Okay, this is basically the die, the IC, right? P-type substrate. Okay, and of course we can easily make our NMOS device. So I'll have my bulk P plus, and I'll have my N plus, and I'll have my N plus. Okay, so and of course I have my oxide here. So this is my gate, this is my source, this is my drain. Of course, drain and source are again interchangeable depending upon which is at higher potential. So I'm just writing it down. So now on this we need to get PMOS device, and it has to be complementary in the sense that all the P should be N and N should be P. So what is done is basically a well is dug, or this is called a well. So this is called N well, which is a N type. This is called N well. So on the P type, an N well material will be formed, and then we start designing the we'll have a P plus, we'll have a P plus, and then there will be N plus, that will be the bulk, and here I have my oxide, So this is my gate. Again, this can be either both source and drain. So this is my source, this is my drain, right? Again, depending upon the potential, this is termed as a source and drain. Okay, so and this is my CMOS technology. So from here I have my NMOS here, and I have my PMOS here, which are fabricated on a single substrate. Okay, so this is a CMOS technology, and of course the NMOS and PMOS, they have their complementary operation. Especially we'll see in the digital circuits that both of these have a complementary function. Okay, okay. So now what is the symbol? As we already have seen. Now see, let's try to see what's the symbol for the NMOS. We already have seen that this is this one. Okay, so I have my this is my gate. This will be my source. Then the current is flowing in this direction, and the drain. Okay, so in case of the PMOS, again this is quite similar. And this is my gate. Okay, so now if you see here, if you remember, here we have seen that the current is flowing from this to this, from source to drain, and source terminal will be showing by an arrow. Okay, source terminal will be showing by an arrow. So this kind of arrow is used. Okay, this is my source, this is my drain, because in this case, as we have seen, that the sources will be at higher potential compared to the drain, and the holes will be flowing from the source to the drain. So please try to analyze yourself. Okay, so that's how this kind of symbol is used. The arrow is used. Again, as I was mentioning, again the source and drain can be interchangeable here, and source means that it is a higher potential in case of the PMOS, whereas in case of the NMOS it is at lower potential. Okay, so now why we can say that these two are having a complementary operation? Why this is called a CMOS technology? Because if you see, like if I consider any MOSFET, right, whether it may be PMOS and NMOS, right? Suppose if I put both of them to the ground, right, and if I want to form a channel, right, in case of the NMOS, I need to apply a positive voltage. That only my electrons will get attracted and the channel will be formed. Okay, so this is the operation of the NMOS, whereas the reverse operation happens, right, in case of the PMOS, that I need to lower the potential compared to this potential of the drain and the source. Then only my holes will get attracted and the channel will be formed. So because of these two being in a reverse operation, right, one has to go in a positive side and the other has to go in the negative side. Because of this property, NMOS and PMOS are called complementary MOSFETs, right? They have a complementary nature, right? For one we need to increase, for the other we need to decrease. That's why it's called the CMOS technology. And especially it is good in the digital circuit, right? When one is turned on by applying a high voltage, whereas if I apply a high voltage in case of the PMOS, it will never be turned on, it is off, and the reverse happens for the NMOS. Okay. Okay, so in the next class we will discuss about the small signal analysis of the MOSFET. Especially we will focus on the NMOS, and once you know how to analyze NMOS, studying PMOS is very easy. It's just a complement.